Well, I was going for sort of a rock star sounding intro to the last video and ended up sounding like Grandpa from Simpsons or something like that. So let's not do that again. Problem 24 is the first projectile motion problem. This one is straightforward because we're launching horizontally. Like that. Um, it's easier. These problems are easier than like full out where you launch at an angle because in this case the initial y direction velocity is 0, so that simplifies a good part of the motion. So this is being launched off a table, although now that I've drawn the table it doesn't quite look like it's horizontal, but it's supposed to be. And there's the floor. Alright, let's define some motion, direction of motion. Let's say that up and to the right. Oh, actually, no, that's not what I did, is it? Is it now? Let's say that down and to the right is positive. Up and to the left is negative. By doing down positive, that just lets me make the acceleration due to gravity positive. We also know that the distance from here to here, from where it first left the table top to where it hits the floor, is 1.52 meters. And the height of the table is 1.2 meters. Anything else? Alright, so this is how I set up. Actually, I'm going to pause for a second because I might have already showed you this back in the notes a long time ago that I recorded. One second. I'm back! So I guess I did show you what I'm about to show you here. This is how I like to set up projectile motion problems because we can separate the motions into two dimensions, x and y. So it's nice. It's a nice way to organize things. So I've showed you this already, so I won't speak as if I haven't, as if this is the first time you've seen it. But let's do that anyway, regardless. Let's set up the two columns. First the x direction, initial x position, final x position. Sometimes I get lazy and I put delta x here. And actually I'll show you the most unlazy way to do this. Initial velocity in the x direction, final velocity in the x direction, acceleration in the x direction, time in the x direction. That's the most unlazy way to do it, but if this is projectile motion, then we got acceleration in the x direction is 0, which means the velocity doesn't change, so we don't need both of these. So really, and we don't need the acceleration if there is none, so we can just go get rid of all this crap and say delta x and vx. Whoops, we really only need these three because again a is 0, which means that the velocity isn't changing, so we don't need to differentiate between initial and final, and we can combine the two x's into just displacement. But we do need all of these in the y direction. Although you could do delta y for this too. I often will. But we do need initial y velocity because that's different than the final y velocity because we have acceleration in the y direction. Time is what links these two lists together, and I probably mentioned that again in the unit or the main concepts videos, but just in case I didn't, time is the link between the x and the y direction. Alright, so let's fill in what we know. We know that delta x, so I said down is positive, so if the ball is moving down, sorry, I said to the right is positive, so we know if the ball is moving to the right, that's positive displacement, so delta x is positive 1.52 meters. We don't know the speed in the x direction. That's what we're trying to find out in part B, and we don't know the time. So we need at least two of these givens to find the third in the x direction. What do we know about the y direction? Well, we know that if down is positive and the ball moves down, we move a positive displacement. So we could say that this is 0 meters and this is 1.2 meters positive y displacement. And again, by putting 0 here, that lets you know often why I'll put delta y instead of y initial, because often initial position in the y direction is 0, so might as well just put delta y and save some ink. And what makes these horizontal projectile motion problems easier is the fact that there is no initial vertical motion, vertical velocity. Only just after it leaves the table will it start to speed up in the y direction, because gravity pulls down with an acceleration of 9.8 meters per second squared. Technically it pulls down with a force that causes an acceleration, but yeah, so we don't know this and we don't know this. But in the y direction we need at least 3 givens to find any fourth or fifth given, and looks like we have that. 1, 2, 3. Perfect. So we can find the time it takes to go along this trajectory by, let's use this kinematics equation. Kinematics also, by the way, is key in projectile motion. Projectile motion is really 1D motion twice, once in the x direction and once in the y direction. So the kinematics work because we have constant acceleration in both cases. Constant 9.8 in the y direction and constant 0 in the x direction. So the kinematics equations are valid. So delta y equals v initial y t plus 1/2 a y t squared, everything in the y direction, because we're trying to find the time here. So this becomes 1.2 equals 0, that's nice, that's what makes these problems easier, plus 1/2 times 9.8 times t squared. I'm just pulling all the givens out of the y column to stick them in here. Solve this for t, and you get 0.495 seconds. So, piece of cake. Now we can find part B, which is the initial speed in the x direction, which is, the question specifically says, what's the speed at the instant it leaves the table? Speed is only in the x direction at this point, so we're looking for this. We can stick these in here now that we know them. 495 seconds, 0.495 seconds. Again, these are what link the two lists together. Now we have 2 of the 3 givens. We can find the third easily with this equation. V initial x equals delta x over t. And that's straightforward. That's just 1.52 over 0.495, and that equals 3.07 meters per second. Alright, the next one though that I do, problem 38, is a bit more tricky because we launch at an angle. We're going to do some extra things there, but not too much more. So, yeah, I'll see you then. Bye, Sonny.